First of all, I'd like to thank the conference organisers, particularly John Lewis, for giving me the opportunity to come and speak to you today. So my name's, as Richard said, Paul Molino. I'm from the Australian Institute for Innovative Materials at the University of Wollongong in New South Wales, and it's a beautiful place to do marine research right on the coast here. I won't talk about what's about 5 kilometres further south. There's a steelworks down there, which is the largest industrial facility in the Southern Hemisphere. But it is a very beautiful spot, and often I'll go down with my students here near the harbour to collect seawater for our cultures, and we'll run into people with boats and what have you down there, and they'll ask what we're doing, and we'll explain that we're working on developing anti-fouling materials, and they'll always ask, so when's it coming? How far away are we from producing these next generation coatings? And it's a good question. Oh, so I think I've got some issues here as well with moving from Word to Apple, but we'll move through it. So essentially there's a whole, as we all know, there's a range of different materials and research that's going on in this area. People looking at surface topographies. Andrew Scardino several years ago provided a very elegant description of the attachment point theory. People are looking at these sharklet type surface topographies that supposedly work via nanoforce gradients that impede the adhesion of zoospores. There's a lot of work done on surface energy, so looking at hydrophilic type coatings that use hydration to prevent protein or microbial adhesion, superhydrophobic surfaces. Still a lot of work on toxic compounds such as cuprous oxide, secondary biocides, as well as some of these positively charged compounds, as well as these dynamic systems, so electroactive materials or chemistries that modulate on the surface. So there's certainly a lot of ideas out there that people are working on, and we're trying to do the right things. So these are two examples of large consortia that are trying to get industry and academics in the same room to try and move towards developing some real industrially feasible solutions to these problems. And these programs have been quite well funded. So the Ambio project, which went on during the 2000s in Europe, was funded to 18 million euro, while the biofouling project, which I believe finishes in November this year, has been funded to 10 million euros. So why haven't we developed the next generation of coatings? Essentially, it's obviously a very, very difficult problem. It's not easy to develop surfaces that prevent the absorption of organisms that have been evolving over millions of years to adhere to all types of different surfaces in the marine environment. And essentially it's been an arms race in the marine environment. You'll have organisms that will develop a way to adhere to an animal or plant, and then those animals or plants will develop countermeasures to prevent them from adhering, and so on and so forth. So it's a very difficult problem. Translation of some of these technologies, very difficult, from the benchtop to a feasible solution. So obviously trying to mimic some of these micro topographies on surfaces in a large scale is very difficult. We need to develop fabrication methods that will assist in this. Chemistry stability, some chemistries are too stable, some aren't stable enough. And obviously cost is also an enormous impediment. But as well as trying to develop methods and new chemistries, I think that there's also a lack of understanding in some of the fundamental mechanisms and processes from both the biological side as well as understanding the different chemistries and materials that we're looking at. So we're still learning the fundamental mechanisms through which animal and plant larvae will initially approach and adhere and stick to surfaces. Microbial adhesion, we're still understanding about the characterizing the adhesives that these organisms use to adhere to surfaces. But we still have a reasonably poor understanding of some of the fundamental molecular mechanisms by which a lot of the systems that we are using in the research work. So an example of that are super hydrophilic surfaces. So these materials have been used for a long time. They've been extensively studied over the last 20 or 30 years for both biomedical and marine fouling solutions. There's three generally understood principles. So we have these long chain hydrophilic polymers such as polyethylene glycol, which binds water through hydrogen bonding around the ether oxygen. They're understood to work by forming a hydration shell, as well as having a steric barrier to prevent the interaction of biomolecules and organisms with the surface. So with this system, the chains need to be long to provide that, that steric barrier. As we know, polyethylene glycol is not very stable in the environment. The second system are these zwitterionic-based systems. Now, these have showed a lot more promise. They bind water through ionic solvation, which is much more stronger than hydrogen bonding, and they're also much more effective at very low or short chain length. So we don't need long chains of these molecules for them to produce a low fouling interface. And then there's these high density short chain hydrophilic chains, or self-assembled monolayers. So we need a very high density of these molecules on the surface to produce this layer that prevents biomolecule or microbial adhesion. However, we generally talk in generalisms about the mechanism of this hydration sphere via which these molecules work. So we do have some understanding about the water that binds to these interfaces. So we do have some techniques such as neutron reflectometry, which will tell you have 1, 2, or 3 molecularly bound or organized water layers above these chains, but we don't have any spatial resolution in the X and Y. So while there's excellent resolution in Z in terms of how many layers there are, so we're looking at sub-nanometer measurements here, we don't know how that looks across the surface. Is it homogeneous? Is it heterogeneous? What's that three-dimensional water structure like? And furthermore, how does that hydration layer, or the architecture of that hydration layer, actually function to prevent the biofouling? So we know that there's many superhydrophilic surfaces that bind water quite strongly, but they are very attractive to proteins, to microbial organisms, whereas others prevent biofouling. So what is it about this fundamental structure of these water layers that prevents their fouling? So there's been a lot of work done in terms of molecular dynamic simulations in this area to understand how water may be structuring around these surfaces, but it's only just recently that the experimental techniques are catching up. So what I want to introduce a little bit today is a couple of techniques which are giving us molecular scale resolution at these interfaces, which are actually allowing us to look at these systems on the same scale as some of the molecular dynamic simulations. So we're able actually to validate these models, and the hope being that if we can understand these systems better via both the experimental and the simulations, we can optimize some of these chemistries and develop new systems that perhaps we hadn't thought of before. So the technique I'm going to talk a little bit about today is atomic force microscopy. So I won't spend too long on this, but I'll just go into a little bit of detail for those of you that aren't familiar with it. So essentially, AFM is a high resolution surface characterization technique. Works very much like a record player. That comparison might be lost on some of the younger members of the audience. But basically you have a short cantilever with a little tip on the end. So this cantilever would typically be about 30 micrometers long. The tip and the end of the cantilever generally have at the very end a radius of around 10 nanometers. So it's very, very small. There's a laser that gets fired off the back of the cantilever and into a photodiode which measures the deflection of that cantilever. Now this cantilever will come into contact with a surface, and if it's imaging the surface, it'll RAST scan across the surface. Now as it moves over a feature, you'll get a deflection in the cantilever that's recorded in the photodiode, and you can get some atomic resolution images of different surfaces. So this is just an AFM image of a polymer film. There's a number of different imaging modes. So contact mode is literally like a record player. You bring the cantilever in contact with the surface, apply a small amount of force, and just drag it along the substrate. So that works quite nicely for hard surfaces, but obviously not so good for soft surfaces where we can deform the substrate. Intermittent contact mode vibrates the cantilever at resonance, usually in kilohertz range. And this, as you RAST scan across the surface, you're looking for changes in the resonance frequency as a feedback mechanism. So this method is much better for soft surfaces. And there's also non-contact mode. So you're actually using other feedback mechanisms such as electrostatic interactions, van der Waals, forces to sit the cantilever just above the surface and scan across the substrate and get a topographic image without actually touching the surface. And then there's this force spectroscopy method. So this is when we're interested in understanding some of the physical properties of the surface. So we can bring the cantilever in, push it into a surface. If we know the stiffness of the cantilever, we can characterize the modulus of the substrate. Or alternatively, if we have a sticky surface, as we bring the cantilever back out, it will provide a measure of the force required to remove the cantilever from the surface. Can give us an idea of the adhesion. So just very quickly, AFM's already been widely used in biofouling research. So one of the seminal papers by James Callow here looked at imaging zoospore of Enteromorpha in fluid. So here we have the adhesive pad and the spore in the middle. This was very interesting because previously most images had been performed through SCM and obviously have dehydration artifacts when taking these images. So clearly the hydrated system looks much more different than what was previously understood from the high resolution SCM images. And also AFM's been used to look at the adhesives of the diatom undulatum. So through this technique we used force spectroscopy to, it's called fly fishing, just to come down above the adhesive. Once we grabbed onto an adhesive, we pulled it back. And what we found was that there were these regular pull-off curves. What these ended up being determined to be were sacrificial bonds within the molecule, which made the adhesive much stronger overall compared to not having these adhesive peaks. So frequency modulation, AFM, is what we use to get these super high resolution images of water structures at surfaces. So it's a little bit different than the previous techniques I just mentioned. These cantilevers are much stiffer. They oscillate in the megahertz range. As they're moving through the surface or towards the surface, they can measure forces in the piconewton range. So that is sensitive enough to measure the displacement of individual water molecules about a surface. We can get the sub-nanometer resolution in the X, Y, and Z. We can look at 1D, 2D, or what we'll call 3D imaging of the water structure about that surface, which all give us different information that I'll talk about in a moment. But the most effective approach is this 3D AFM technique, which gives us a measure of the hydration force field about a surface. So this technique was really pioneered by one of our collaborators, Takeshi Fukumi from Japan. So in 2007, he initially used this technique to look at water layers above a bilayer. So what he did here we have the frequency of the cantilever as you approach the surface. So consider the surface being at the left side of the graph here. So as he approached the surface, we get a sudden, a small increase in the frequency, which means that we're pushing against a molecule, and then we punch through that layer until we start to apply more force to a second layer, and we punch through that again. And if you have a look at the Z distance between these peaks, it's about 0.25 nanometers, which is actually the width of a water layer. So this is 1D FM, AFM. He also used the 2D technique to scan across the surface. And what he found was, although the system was a little bit unstable, he would actually punch through discrete organised water layers at the surface. So different to bulk water, these layers were quite discrete, organised, and with every sequential layer, the water was bound a little bit more tightly to the surface. So moving on, this is a nice example of this 3D AFM approach. Here Fukuma looked at the hydration layer of mica, which is almost atomically flat. It's of interest to people looking at cloud seeding and the hydration of clays. So what we have here is a force field around that surface. Up here we have unstructured bulk water, so there's just hydrogen bonding between water molecules up here. But as we approach the surface, and we know the crystal structure of these substrates, we actually get a discrete layer of organised water about 0.25 to 0.3 nanometers from the surface. Now, if we have a look at a cross-section through that layer, you'll see at 0.31 nanometers above the surface, we have a homogeneous type image of the force field, which means that it is an unorganised layer. As we move through towards the surface, you can start to see these discrete structures. And again, this is an average of a 1D approach curve on the mica, and we just have a single water layer. Because the resolution is so high using this technique, we can actually associate specific molecules on the surface with the water interactions. So here we have an increase in the force, which was determined to be individual water molecules actually binding to an OH group on the surface. Now, the aim is to start to use these techniques to validate a number of models which are being widely used in trying to develop or imagine new and interesting surfaces to prevent biomolecular and microbial adsorption to surfaces. So this is some work that has been performed by another one of our collaborators, Professor Irene Yarovsky at RMIT University. So she's a modeler and was looking at surfaces that presented organised hydrophilic and hydrophobic chemistries at the interface. This will look familiar to you. So this is the density of water according to the model approaching these surfaces, and here she has two discrete water layers. Because now we have a method that can validate these techniques, we can take this ideal system and confirm or dispute her specific model. Down here is an example of a footprint of an adsorbed protein used by fungal spores to adhere. So depending on the width of these hydrophilic and hydrophobic rows, she found that either you have a large adhesive footprint of that protein on the surface, or you have a low adhesive footprint. Of course, the lower footprint is determined to weaken the overall adhesion of the protein and impede its self-assembly into rodlets. So the big questions that we want to use this technique to answer really are, why are some hydrophilic surfaces resistant to bioadhesion while others are not? How does water structuring at the interface participate in this process? Can we use these systems to design inorganic based surfaces which perhaps are less resistant to degradation in the environment compared to some of the carbon-based systems that we're using, and of course learn and optimize. And just to finish off, I'm running at a time here. Of course, the modelling of protein interactions with surfaces has been undertaken for quite a long time. A lot of these models work on the scale of nanoseconds, so it's very difficult to develop an experimental technique to experimentally record these processes. However, using high-speed atomic force microscopy, we think that we're getting closer to, again, understanding the fundamental interactions between some of these adhesives that are used by these microbial organisms or cells with different surfaces. So I'll just rush through these slides a little bit because I'm running out of time. However, high-speed AFM, essentially we can record an image in about 100 milliseconds compared to standard AFM, which takes anywhere from 5 to 20 minutes. We can get quantitative data in the X, Y, and Z, as well as visualize the dynamics of these processes, as opposed to most AFM images that you may have seen of biomolecules interacting with surfaces where those samples generally need to be completely dried out in order to image them. We're able to get sub-molecular resolution, which you'll see in a moment in a couple of videos. And the biomolecules that we're measuring have not been modified. So there's a lot of fluorescence-based techniques that people can use to image proteins on surfaces. However, you won't get sub-molecular resolution using those techniques. It's just more a matter of are the proteins there or not. So it's an on or off type measurement. So here on the left we have a high-speed AFM image of Fibronectin on mica. So Fibronectin is a model protein for biomedical-based studies. This has been sped up a little bit, but if you have a look on the right here, so these are individual proteins on the mica surface. This is 190 nanometers by 90 nanometers, and as you can see, the proteins just don't bind statically to the surface. They're quite dynamic, they'll move around, they'll change conformation. We've undertaken a number of studies where we've identified several different conformations of proteins and a number of different mechanisms in which proteins will interact with each other to form larger adhesive structures. So this video was on a atomically flat surface mica, just to prove that we can also image on polymer surfaces. So you'll have to trust me that this is much less blurry on my computer than it is up here. But this essentially, I'm happy to show this to anybody later on my computer, but essentially we're able to measure rough polymer surfaces. There's no protein up here. Down here we've introduced proteins, and you can see them moving around, changing conformation. They're quite a dynamic system. So I think I'm just about out of time, so we'll using high-speed AFM, we're hoping to understand some more of the molecular mechanisms underlying the interactions between adhesives used by biofouling organisms with different surfaces. We're hoping to understand how different chemistries influence not only the binding and organisation of these adhesives, but as well as their diffusion about the surface. How long do they reside near the surface before they actually find a way to adhere? And of course, we want to optimise some of these surface properties towards impeding some of these processes. So I'd just like to thank some of our collaborators, particularly Takayuki in Japan, who helped with the high-speed AFM, Associate Professor Michael Higgins, who's an expert in bio-AFM, Lei Feng, who took the high-speed AFM videos, our PhD student, and thank you all for listening.